Okay, go ahead. It's yours.
Sure, thank you. So you could see my screen, right?
Yes.
Okay, I'm gonna hide the floating meeting controls. Okay. Okay, so I will, our group, I have watched some videos from other groups' presentations, and then I noticed them that they all spent more than 5 minutes. So I would like to know if it's okay to pass the
It's
5
probably
minutes.
okay. Yeah, because if other people, I didn't stop most of them, I probably shouldn't stop you as well.
Okay. Yeah. Anyway, but we will try to make sure that we will fit into the 5-minute slot. Okay.
Appreciate that.
Yeah. So what we have done is kind of like eager mmap. We re-implemented. So the program statement begins with mmap system call. So we re-implement mmap in a kernel module, which let the mmap to do what we want. So to be more specific, we call it eager mmap, which allows the user to eagerly request a contiguous chunk of physical memory. But there might be the case where fragmentation occurs, which means the allocated physical memory is not necessarily all physically contiguous. So that's why we need to handle the case where we eventually get several chunks of physically contiguous memory, but those segments are not all contiguous. I mean, for each segment, they are contiguous, but overall segments, they are not contiguous. So because the motivation is we would like to leverage the devirtualized memory such that virtual address is equal to physical address. And we are kind of porting that into the RISC-V ISA, but we haven't done that yet. So the only thing that we have now is the mmap version without the devirtualized memory working, which means we still have to go through the page table to do the address translation. But although physically it's not necessarily contiguous, but in virtual address space, it is indeed contiguous. Because the user could just view it as a contiguous chunk of memory, although physically it's not contiguous. So now is the key issue, which will be presented by Chen-Fei.
Excuse me. Hi, everyone. So I would like to present the key issues. So actually, as we all know, when for kernel programming, the most difficult part is actually it's so hard to find resources for help. So at first, we came into the issue that we were not sure about which API to use. So we went through Stack Overflow for questions. Also, we checked some Linux kernel patches and also documentations. However, some of the documentations were out of date, so we could not follow their directions. So we also checked the Linux kernel mailing list to make sure that we have got the most up-to-date documentations of APIs. And then after implemented the APIs, we came into the issue of debugging. So when allocating the pages for users, at first we tried to run up to reach to the desired number of pages, but we failed. However, when kernel programming, there's another difficulty that when we came into the bugs, we don't actually know where the bug is located. So we have to find the bug from small parts. So at first we allocated the really small amount of pages, and then eventually when we increasing the number of pages, we found the error. So instead of trying to running up for the pages, we try to run down the number of pages, and then we fixed the bug. So yeah, that was the basic issues that we encountered. And if you are interested to know more, you can ask Yusen more about it in the demonstration.
Yeah, so here's the result and analysis. So in user mode code, the user could just directly call mmap to eagerly request a chunk of memory. So in this case, we could see that it is 40961, which equals, because each page size is 4096 bytes. So since if there are 10 pages, then there should be 40960. But since the user passes in another one, so indeed we will need 11 pages. So from the output, I don't know why my cursor is not showing up, but if you could see the picture, the screencast below, we could see that there are several output, and we could notice that at first the kernel space just print that the user wants to mmap size, which is 45,000 and then 56 bytes, because it is exactly equal to 11 pages with 4096 bytes per page. So that number of pages is 11. And then it will allocate 8 pages first, and then 2 pages, and then the last one. So after each allocation of the contiguous pages, it will do a VM insert page, which will create the page table. And so for the testing code, what we did is, so as we can see in the screencast, there's a for loop. The for loop indicates that we would like to traverse the unmapped area from the beginning to the end. The reason that I set the upper index, the upper bound of the index to be 5632 is because we did a simple calculation, which because we treated the unmapped area to be an array of unsigned integer of 64-bit, and we just did a computation, and we found out that there are 5632 integers, and we just simply tried to access that by writing 1 to that, and no segmentation fault. But later, when we try to just increase the upper bound by 1, which means there will be a segmentation fault because we actually didn't unmap to that specific area, and we try to reach just reach one index right after that the unmapped end address. So that will cause a segmentation fault. And so in our you could see that on the bottom there's a kind of like segmentation fault which showed up at the end. And in the middle, it prints out the values of the registers, which just to indicate that there is a segmentation fault. And so now let's take a look at how our unmap works when user wants to request about 10,000 pages. So I'm gonna, so you could see my screen now, right? Hello?
Yes, I can see your screen. Yes.
Okay, great. So now this is the kernel module that I wrote, and I'm gonna load it. And then I'm gonna go to user testing code, and then, so this is the testing code. And so I basically, now the size I passed in is this large, which is 4996 times 10,000. So it's gonna allocate a bunch of pages. So we could just type make and execute. Oh yeah, so we could just ignore all those outputs that serves as the debugging purposes, and we could see that. So from here, this is the user space, user virtual address, and this is the unmapped size, and which is what we want, exactly what user passes in. And then I will first try to allocate order of 13, which is 2 to the 13, which is 8192, but it just failed. Because in kernel space, there's a one line of code which defines the max order that we can allocate. So we could see that even if we pass in by 11, it still failed. So that's why the only we could allocate the largest part, possible part, given the current kernel is 1024 pages. So that's why it ends up being, we allocate 1024 pages in several times And then we end up allocating 1024 plus 512 and then 256 and then 16 pages at last. And so this is the allocated pages. They are not physically contiguous, but within each segment, they are contiguous. So that's why the user could later access this using iocto, which is IOCTL is another system call, which we could also re-implement that in our kernel module, which serves as the purpose. And with DVM working, what we would get is exactly the same as like this, except that the user could get a list of contiguous memory, and the user could just access those pieces of memory using readv or writev system call. But we haven't done that yet because I haven't integrated the DVM code, the virtualized memory code. So this is the whole demo, and yeah, and that will be all. So yes, so I'm gonna stop sharing here. So anyone has any questions?
Okay, thank you, Yusen, and also thank you, Chen-Fei, for presenting this work. So let me think what I want to start. So I have a question. Why does people call this eager mmap?
I call it.
What? Yeah. Why you call it eager?
Because for my previous implementation, it is when user tries to load the kernel module, we have a PCIe device that is simulated in QEMU, and then inside that PCIe device, it sort of acts as a computing device or some near memory accelerators. And then in my PCI probe function, so sort of like when we load the module, we would like to probe for the device. And so while probing the device, as soon as we figure out we have found that device, we would allocate a buffer. And so previously, what I did is, could you still see my screen?
Yes.
My virtual machine?
I can see your screen.
Okay, so so here is my so this is the original implementation, which we sort of implement. We allocate buffer at the beginning, and then we map to those buffer using remap pfn range, that kind of function. So which is sort of like we allocate buffer at the beginning, and then we allocate buffer at boot time, and then when user code is running, it basically just map to that area, map to the pre-allocated area. But now, instead of allocating all those pieces of memory in advance, what we did is to let user tell the kernel how much memory we want, and then the user and then the kernel will respond by calculating how much memory and the number of pages, and then the kernel will call alloc pages, and then to create the page the page table, and then to sort of so that's sort of like the why we call it eager paging instead of to allow the user to request any amount of memory, and our kernel module will be able to respond to satisfy the user's requirement.
Okay. All right, thank you. So a follow-up question. In your kernel code, do you you have a page table? Maybe I ask the other question first. I'm interested to see the performance difference between purely physical memory, which means you are contiguous physical memory, versus you have to do memory address translation, which is the virtual address, like what your current implementation is. How much performance difference will be there, especially when you're looking at the performance of the cache?
Honestly, I am not sure because there is a paper talking about the virtualized memory. And in that case, they sort of talked about the overhead of the address translation has been reduced to 2%. So it is huge reduction in the critical path of the memory access. And also the reason that they want that's sort of like the virtualized memory is because for some big memory workload, like on some server, they would like to, I mean, for big memory workloads, they have some specific characteristic, which is they rarely swap, and they sort of pre-allocate a big chunk of memory at the beginning, and then they just do not swap. So there's a paper talking about it, and I have also got another PPT, but I would say it's not, yeah, it's not appropriate. Okay. Yeah.
So my question is that really about cache miss. So when you have a cache miss with physical memory, because when you have a cache miss, you're trying to get from the physical memory, and you don't need to do address translation because you directly can get it. Right. But versus virtual memory, which is you actually going to, you need to do actually address translation, probably only once, I assume. You access to the page table once, and then you basically get it back, right? So so it's really the address translation is one access to the page table. This leads to my next question, is that I assume you understand the difference between page table and the inverted page table.
Oh, sorry, I don't really understand inverted page table.
Okay, so so page table you can think about is that you actually translate from the virtual address to a physical address. That's the page table.
Yeah.
So page table will give you that. So inverted page table is that you actually give me the, let me see, inverted per page table. Okay, I know what's the difference. So when you actually want to do translation for the page table, means that every single page entry, the virtual page entry or physical page entry, need to be in that page table.
Yeah.
Okay, so the page table usually is pretty big, and the page table itself cannot be put in the cache, has to be in the memory somewhere. Inverted page table is that only keep those page table entry that's actually in the cache.
Oh.
So essentially the inverted page table is allow me, it basically using the associative array. So essentially when you want to access a virtual page, that I will go to inverted page table to see if it's in the cache.
Yeah.
So the thing is, in terms of try to identify whether the address in the cache is going to be really fast, because you're using inverted page table. Just to let you know, inverted page table, the number of entry in the inverted page table is proportional to the number of pages in the cache memory, essentially. So it means that not all of them. So I don't know about your the operating system you're using is using inverted page table. You might want to check, because I know a lot of the modern virtual memory, they have been using inverted page table a lot, because inverted table performance is supposed to be faster for kind of doing this address translation. But I forgot whether Linux is doing that. I forgot exactly. FreeBSD, I remember they have both. But I'm not sure about Linux. So just let you know the concept inverted page table And with inverted page table, you only pay the cost when you have a cache miss. So in other words, when you don't have cache miss, the physical address and the virtual address is giving you very, very similar performance. I don't know about that 2% is actually using IPT or not. So if you look at IPT, that's inverted page table. That's how they actually designed it. Yeah. Okay.
Thank you. And also, I'm thinking about if for any virtual address is exactly equal to the physical address, then we don't even need to have to go to the page table to do a page table walk or even go to the cache. We could directly send that address to the CPU, and the CPU would just use that address to access either the cache to see if it's a cache hit or miss. If it's miss, then it will go to the second level cache. So I think what we are trying to optimize is the path, because address translation can be an overhead if especially for the big memory workload where there sort of could be like terabytes of memory. So there will be cache misses even if we are using inverted page table, even though the workload could have a lot of spatial locality. But I think using the virtualized memory would be at least outperform the inverted page table. And
hey, I suddenly forgot. How do we actually detect cache miss? We just try to access through the cache memory and then find out it failed. Then that's cache miss, or do we have to check a table? We don't have to check the table, right?
When we issue an load or store, which we have an address, that is a virtual address, and then we need to first go to the TLB. And if it's TLB hit, then we will just return and then to pass it to the cache. But if it's a TLB miss, then we need to go to the page table and then do a page table walk to do the address translation. And then we get the actual physical address and then pass that to the L1 cache. And then we could get either it's cache hit or cache miss. If it's cache miss, then we need to go to the L2 cache. Yeah.
I see. Yeah. Yeah, I'm actually even forgot how L1 cache, L2 cache, how they actually do this translate, because the performance, as you said, the work I'm actually thinking is you guys are doing great work, and getting it to work, that's actually very important. It's just how you're going to measure the performance difference between the whole system, whether how much is going to save you here and there. I think that is the major issue you need to address when you want to write a paper or something like that. Okay.
I think our purpose is first just provide a convenience for users to allocate a bunch of memories. And also we haven't think about this so far. But first, we would like to have it work. And as for the inverted page table, as you mentioned, we would do more research after this. But thank you for your advice. So I think the next step for us would be probably test the performance and probably make some speed ups as possible. Yeah.
Okay. Yeah, that sounds good.
Yeah, we are thinking about porting it using Gen 5 simulator to measure the performance. Because currently we're only using QEMU, which only emulates the behavior, not the actual performance. It's not cycle level accurate simulator. So that's why we need to use Gen 5 to get the most accurate data.
Okay.
Yeah.
Okay, that sounds good. Okay, that's great. Thank you for your hard work. It's a very, very interesting piece of work.
Yeah.
Okay, thank you.
Thank you.
You're welcome. Thank you. Next group will, I know there is one group who's supposed to start at 4, but you say you wanted to start it immediately after, right?
Yes, Professor.
Okay. Anurag, who is actually in your group?
Avish and Greasy.
Hi, Professor. Yeah.
Let me see. Let me actually write it down. This
Yes.
is number 12.
Yeah.
Avish, Anu, Rock, and who else?
Greason.
Greason. Okay.
Yep.
Okay, and three of you?
Yes. Yes.
Okay.
Professor.
Okay, go ahead. You can share your screen.
Okay. Okay, can you see the presentation?
Yes, I can see that.
Okay. So me, Anurag, and Greason are going to be presenting our presentation of the project. And our project centers around securing and a secure and private storage of a user's purchase history. So the problem that we're trying to solve is the unsecured storage of purchase history. So typically when a user purchases something from, say, a grocery store, that information is saved on public cloud servers, which are prone to attacks and leaks. And even if the information is secure, it's typically not encrypted, which means that the information can easily be exploited to target customers based on their behaviors. So the question is, how can we ensure that a privacy conscious user has his or her purchase history private and safe? And this solution must also include situations in which someone needs to access that purchase history if they, for example, want to return an item, or if the grocery store wants to provide an ethical discount. And so the solution that we came up with was inspired by EthicOS. We plan to create a secure framework through which users would have their purchase history stored privately and securely. By ensuring proper encryption of the purchase history, an account's history will only be able to be viewed or changed with the express consent of the user. This provides users with full agency over their purchase history data and includes a human element in the computation of returns and discounts. So a practical application of this would occur in like grocery stores such as your Safeway or Target, with the store providing the customer with a card that contains the encryption key to their purchase history. And without this card, the store would be unable to decrypt the history, which makes the data unusable unless that card is specifically present. So this physical encryption key is useful in ensuring that the physical presence of the account user when any sort of computation is needed.
Avish,
Hmm?
Avish, I just want to let you know your note in the presentation is actually on the screen being
Oh, it is.
recorded. Yeah, for me, I see. Yeah, that is the window is there.
Oh, okay. I didn't
It
realize.
actually blocks some of the text.
Oh, okay.
That's why I'm a little bit worried. I mean, it's okay to show it there. Yeah, this will be nice.
Okay.
Yeah, because I can read the slide. Okay, go ahead. Thank you.
Okay. And so kind of to add on to some more specific details, the encrypted data should only be stored in a private network of the store and not on any sort of public network or system. Also, there will be functionality included which allows the user to only decrypt purchase history of specific categories if they want. So for example, if they want to decrypt their produce and dairy history, but not their alcohol purchase history, they would be able to do so. This is useful for returns where obviously you need access to the purchase history, but if you don't want to decrypt everything, you can decrypt only specific categories of history.
So we want to ensure that the customers keep their purchase history pretty private. So we want to ensure that they keep the encryption seed so that the market or the store itself cannot end up viewing certain purchase histories at will. So the customers only provide the seeds only when they want to end up doing something like making a purchase, when they want to return items, or if they want to take care of categorical or loyalty-based discounts. Next slide. So looking at the actual flow of this, our main implementation has 4 different kind of functions in a sense. So basically our customer is able to, with the use of the secret key, is able to create new customers, create new orders, process returns, and get these discounts. So this is just generally how it looks. Next slide. So our future aims are that because we keep this as kind of like two-sided, as just the store on one side and the customer on the other side, we want to ensure that the companies don't end up storing the encrypted data, because certain companies, if they are tending to be a little bit more malicious, they could possibly end up trying to either end up doing attacks or end up passing the encrypted data into third parties, which might not necessarily be very useful, but if one third party wants to attack that data, that's also kind of an issue. So one of the solutions to this is to possibly end up like having a trusted third party middleman that could kind of hold the encrypted data and like take advantage of the communication on both sides. And also, we want to ensure that our system crashes do not end up messing around with the re-encryption that we end up doing automatically after each method is being enacted. Next slide. So all of our code can be found online at this link. And I think at this point, we might be moving on to our demo.
So yeah, I'll present my screen for the demo. Just give me a few seconds. Yeah, so my screen should be visible now. And Professor, for this demo implementation, we have kept the thing simple. We are just showing that we can actually encrypt the data and then decrypt it and then make changes to it, whether it's for returns or it's for discounts, providing discounts. So right now we just have one server and one client implementation, which is written in JSON RPC. So I'll start the store server, and in the store client, we'll see some flows. So as soon as the client starts, we see that we create a customer, and then we ask for, if this customer is newly created, we need to assign some key, which, so we ask for a random input from the customer, and the customer inputs some random key, and then all the other flows happen. So if we go back to the store server, right? So first thing is that we generated the key, then we generated a random order. And if you see here, the order details are encrypted. So for now, we have kept the category not encrypted, just for making things simple. But item name, item ID, and cost, and all of these are encrypted, in the sense that you do not have any form of open purchase history of any particular user in your system. But let's say you have to again process return for something. So here what we do is we, if I go to our server.cpp and we go to process return, we see that we first decrypt the order based on the key provided from the customer consent, and then we create and then we modify the order, but the only order which we are storing back is the encrypted order. So the decryption is just for verifying whether that item was actually present there, and or all sort of logic which you have to build on top of that. But in the end, the only order, if you see here, there were two items. After processing the return, we are left with one item, and that one item still, that's data, is still in the encrypted form. And the same case is with the providing the discounts. So again, this process is more or less the same. We are just displaying for the sake of for the sake of visualizing that the cost was reduced from 10 to 9.5, and we saved $0.5. But in the end, again, the order stored here is in encrypted form. So the more or less the whole idea is that your order to the retailers, to the wherever it's stored, it's private intranet of the stores, is not stored in an human readable format. It's always encrypted. So even if there is some attack, or you need to target some customer behavior applying law, you cannot do that unless and until you have the key of a particular user, and unless and until a customer is involved in some sort of competition, whether it's returning the items or it's providing discounts. So yeah, this completes our demonstration for the presentation.
Hey, that's great. I like the your project. I like the idea. As you guys already hinted, that what you propose to do is going to change the way people doing micro targeting.
Yeah.
So you understand what do I mean by market? Oh, sorry, micro targeting, right?
Yeah.
Yeah. So I just want to clarify. This is what I got from you, is that the traditional advertisement company, they, instead of doing whatever they're doing with micro targeting today, they're going to share some of the discount with the user who use your assistant, and in order to obtain their data to do micro targeting, if I understand correctly. So what do I mean by this is that we raise the cost for them to do micro targeting. So it used to be micro targeting. We're looking at individual user, their transaction data, their purchasing data, and for us to decide what we need to predict, right? The next one. So right now we hide the data. They no longer have that predictability, is no longer. On the other hand, I remember I heard you saying something like, if I'm going to let them decrypt my data or portion of my data, you need to give me some discount or something, right? So essentially, of course, you give away the data, you can actually get some discount. To me, is a grabbing away some portion of the profit that you would have made on me. Now you actually be able to. So essentially, I offer the data, and you recommend a product to me, but with less profit margin. That's the way I interpret the business model that you're talking about. Is that right?
Actually, it's a bit different, but yeah, this is somewhat similar what you said. Actually, our business model would be like, if you are a privacy conscious user, why would you go to other stores for buying your stuff? Instead, you could come to a place where your purchase history is encrypted. And the second thing which you told about the discounts, yes, the discounts work here in different ways. It's not as that we can we have the previous data so that we can have some target some customer, we can do micro targeting. But here the discount, the margin will be less, and for providing the discount we'll have to ask for customer consent, that if you want discount based on this category, are you willing to us to check whether you are eligible or not for this discount based on your previous history.
Right. That's an eligibility issue.
Yeah. So are you willing to, let's say we have a algorithm which checks the past order history of groceries, but then we need for a customer to ask, hey, are you sure that you're gonna we can give you the discount, but we need to encrypt it. But then again, professor, we are just only decrypting the information just for running our algorithm. The algorithm is not messing up, not doing any recommendation or something. The recommendation is logic is already there. And again, we are storing back the data in encrypted form. So the only thing the algorithm is doing is to just have some sort of logic on the previous data. So the data itself is secure, it's encrypted, so you cannot mess up with that. So any form of micro targeting will be really difficult unless and until you are malicious yourself, like a store is malicious and you are not, while you are decrypting the data, you are doing some sort of another computation which you are not supposed to do.
Right. So one of the idea, I mean, the thing is, I actually, personally, I like your idea. I like your idea to provide this protecting the customer, but the resistance of your idea is exactly the advertisement company saying that now we lost the advantage, be able to sell more, because now we try to, you guys try to protect the customer, and they feel that, well, actually Safeway, it will be okay, but the advertisement company like Google and Facebook, they might be in trouble, in my opinion. I mean,
Yeah,
because
yeah.
they're the company who is doing that. So I'm actually thinking whether it's a possible, I don't know if you are familiar with some of the modern machine learning technology, is that I might be able to provide some data set about myself in the way that micro-targeting is not exactly micro-targeting, but it's actually can do some kind of targeting, because obviously they cannot see all my data, but they can actually provide some kind of categorical result. They can recommend which they can still make some money, but it's just we actually protect the interests of the customer as well.
Yeah, and the other thing which this could happen, yeah, some sort of computation can still go on, but let's say if you are a customer who doesn't even want to, for one of your categories, to get your data decrypted. So let's say for alcohol, if you don't want the discounts at all, so that's entirely impossible now, because they don't have any data of the alcohol category you have. They just have the grocery and deli, which should be fine, like grocery and delis, but the sensitive data is still like encrypted. So that could work, but of
Right.
course, yeah, sophisticated machine learning algorithms will still be able to find something with other categories if given.
No, I think economically, what you guys are proposing is intriguing to me, because essentially we are denying the capability of micro-targeting,
Yeah,
which itself might be a good thing, because micro-targeting, in some sense, people are arguing it might not be ethical,
yeah,
because we're triggering the economic behavior based on private data. But it actually can improve our users' experience in purchasing, and such that we boost the willingness to spend money to do the purchasing or commerce, and which actually it might still hold up the same level or even more level of economic behavior. It's just some of the company won't be able to do the same kind of business.
yeah,
I would say like Trader Joe, Safeway, or Walmart, they should be even better, but and they probably can save some advertisement costs in some way, which I think is actually a good thing, right? Because those companies will be able to dedicate the resource to develop more product instead of
yeah,
spend more
yeah.
time on the advertisement. Yeah. No, I think this is an interesting topic, and we definitely worth to push it. Okay. All
Okay.
right. Thank you very much, and
you.
I appreciate the effort and the time you actually look into this issue. It's a bit controversial, but I think it's very important. Yeah.
Yeah.
Thank you.
Thank you, Professor. We have one more small request to make. Since one of our group members will not be available after tomorrow, maybe because he's traveling. So we were hoping if you could give a homework presentation in 5 minutes right now, or after this other group has presented to you itself.
Okay. So after next group, you have 5
Okay.
minutes. But
Okay.
I'm going to turn off the video first,
Sure.
because
Thank you.
I don't want the homework grading be included in that.
Sure.
video.
Thank you so much,
Okay.
Professor.
You're
Appreciate it.
welcome.
Yeah.
Yeah. Okay, please unshare your screen. Okay, next group.
Hi, Professor. Can we share our screen?
Yes, please. So this will be Xiaoxi, Haoming, Xiao, and also who else is, and Fu Ming, is that right?
Yes.
Okay, let me actually write down your name. Okay, go ahead, please.
Okay, Professor. So before we started, we will say that we want to about the project. We want to build a scenario, an application environment of the two PCs. So this project is about the music generation, storage, and the broadcast system with two PCs. And here you can say a simple graph about our project. So you can see the left part is about music generation part. We want to say that we want to meet the different like the different music styles of the clients wanted. So we used the machine learnings based on the variational autodecoder architectures to generate different styles of music, and then after the music is generated, it will store to the servers in a different styles like the strings or other things. And you can assume that if you are a client, you want to play the music according to different styles you like, you can just grab it from the servers and play it. The next is you can see is the simple flows of our entire program project runs. The first, we will initialize our GFS, and our music generators will generate music and based on the different music styles, and it will convert the music to the strings, and we'll upload it to the servers, and the servers will store the music based on the 2PC protocols. And if the clients want to require the music files, it will just grab it from the servers and play it locally on the client side. And also, we think we also achieved some interactions of the JSON 2 PCs between the Python and the C++. It's all of ideas about our projects. Can we show you the demo of it?
Sure, go ahead.
Oh, so can you see the screens? Let's see the top left and
No, sorry.
Yeah.
Can you share the whole screen? We share and share the whole screen. We cannot see your screen.
And now we
Yeah,
can only see the
I only
browser.
see the PowerPoint
Not
slide.
the whole screen.
Oh,
Yeah.
sorry.
I can only see the PowerPoint.
Slide. Yeah.
Is that okay now?
Yeah.
Yeah.
Oh,
Looks
let's
good.
assume the left part, the up is for the music generation part, and it's the music generation files. Let's assume that we want to we wanted the machine learning to generate it adjust music, and it will upload it the weight. We trained it and generated a JS file, a JS music, and it will upload it to the server part, and the server part is on the Fuming side. We don't show it now. And for the right part is about the client. Let's say assume the client we want to listen the JS music, and it will grab it from the server, and it will have this JS receive WAV music files, and we can listen to it now. Can you listen to it?
Oh no, can you also share the sound?
Oh, sorry. Can you listen to that?
Yeah, I can hear that.
Oh, sorry about as there were a little bit noise about, because we didn't train too much time about our neural network. So this is all of our ideas about this project, and about the server part, you can see it's showing on there.
Right.
It transfers the music to some strings, and in the client part, it will convert the string to the music file.
Okay. So what? Can you go back to the slide number 3?
Oh, yes.
So what machine learning algorithm you were using?
We
to-
use the algorithm called the variational autodecoder architecture. Something like it will store the rhythms and the frequencies of the music and encode it.
Does it doing some kind of natural language processing on the lyric or just the music?
Just the music.
Okay, just the music, not the okay. Yeah, so it's basically looking at the rhythm to
Yes.
decide what style of music it is. Yeah. Okay. Do you think that's enough? Should we do not just about the music, but look at the style of the singer, or is a female, male, or what style of a production? I mean, this might not related to operating system, my question, but I'm just wondering, what does the industry, say company like handle this kind of music business about music sharing? They need to do something, right, to process the
Yes.
content in order to make a recommendation. What kind of neural network they're using? Do you have some idea?
I think maybe our algorithm can do it, but it needs a lot of trainings, and maybe it will use some another algorithm. Don't you know it's about the GANs, the GAN neural network? Maybe okay, I think.
Okay. I'm just thinking that this is interesting because I know that for example, you probably heard about BERT,
Uh,
the bidirectional. It's basically for NLP, but people use that to prediction of movie. So looking at the movie and then decide whether it's a prediction about the recommendation, not music, but because in movie you have different kind of combine of the natural language processing with other with vision capability, and so some of the work there is interesting. Yeah. Okay. Let me actually think about the other question. Okay. My question to you also is that in your scheme, is there any privacy consideration you need to worry about? So for example, your step number 5, right? You said when the client requests music file,
yes.
the server will find corresponding chunks, right? And then the return with the music file. Will number 5, some of the data be used for step 1 to 4 in the future? Is my question fair about your system?
Sorry, I'm not quite understand.
Okay, so this slide, what is a step number 5? Step number 5 is the client request certain music file, right?
Yes.
Okay, so that basically provide a data point for this particular client. What's their preference? What's his preference about what type of music that he would like to get? That's why he's actually requesting, right, the music file.
Yes.
And this is a data that could be learned, just like a previous group. They're looking at purchase history, that this is like a purchase history of music. So is there any thought for you to try to protect this part, or actually that's totally out of the scope?
Professor, I think I can answer this question about privacy. May I?
Sure. Fuming, go ahead.
Yeah, I think since we want to store a music file in 3 copies, that means you have 3 servers to store the music file. So every time the clients want to request some music files, it may access, random of the server. So if the company want to record the time they request the music file, and the type of the music file, the record could only be stored in one of the server. But next time, you may ask one of the 3 servers to access another music file. The record on all 3 servers are different. So it seems like that we split the privacy to 3 parts. Only when you take all these 3 parts together, then you could get the full privacy of a single user.
Okay. All right. Thank you very much, Fuming, for your explanation. Okay. I like to think about a little bit more about what you have been doing. I'm actually interested in the this domain of music. How do you actually store the music? How do you actually retrieve the music? I think it's an interesting domain that we see industry have certain company focusing on this domain. So I just wonder if you can just email me your PowerPoint slide. I would like to think about some of the point. And but other than that, you don't have to worry that you're doing great as a presentation. Yeah, I appreciate that. Okay, so this thing, Fuming, Haoming, Xiaoxi, and Xiaoxiao, have you done your number 2 and number 3? You're done
Yes.
done with that, right? Okay.
Yeah.
Yeah.
We
So you don't have to
presented
worry
it.
about that. So I think you can just relax, and I'm going to turn off the recording. Then I'm going to grade the other group, which is the gentlemen are still here. Okay. Okay. Thank you.
Thank you, Professor.
Thank you,
Professor.
Professor.
Thank you. You're very welcome.